she don't see the light that's shining deeper than the eyes can find it. Maybe we're made of blind, so she tries to cover up her pain.
Now let's get to this idea and this concept of boiling. We've all seen and heard and talked about it most of our lives, but we really have it kind of improperly put into our head of what's going on. It's caused by a certain set of conditions. And the boiling point, we have to remember this, the boiling point itself is a temperature. It's the temperature at which boiling occurs. But that's not what boiling is. Boiling is not a boiling point. Boiling is something different. It's specifically when the vapor pressure is equal to the pressure pushing down on the vapor. So in this case, we've got a lid and it's got some weight to it, and it's pushing down via gravity, pulling down on it against all these molecules that are in this container. And if these molecules, if these little blue gas molecules can push on the container up at the same force that the container, that the lid is pushing down, then we've reached the point where we see boiling. This can happen not only as a lid, but it could happen if we remove the lid and we imagine what's actually going on inside, like our containers when we are cooking food. The pressure down is caused by the atmosphere. So here we've got these air molecules. There's no such thing as air molecules, but you know what I'm talking about. We've got this atmosphere pushing down, and the gas particles here that we have coming out, the vapor, it has to be able to push this gas away. And for it to occur, the pressures just have to be equal. But that's not how we normally see it when we see boiling occur in our kitchen. Instead, what we see is something more like this. We see an energy source at the bottom. This energy source at the bottom of the container will get the molecules at the bottom of the container hotter than the molecules at the surface. So what happens is we can get these little temporary evaporations going on at the bottom that don't last. What happens is a bubble's created at the bottom. Here's this bubble, and it's filled with some of the molecules of the gas that have evaporated. So it's filled with some of these little evaporated molecules, and they start to push out on the molecules around them that are in the liquid phase. If the inside pressure can push just as hard as the molecules in the liquid are pushing, then that bubble can float to the top and pop and come on out. At that point, we see the boiling that we normally experience in the kitchen. So boiling is quite interesting. It's the ability for the vapor pressure to push away whatever external pressure there is in the system. That external pressure could be the atmospheric pressure, in our case air, and we see these little bubbles that start to form during the boiling process because the heat source just happens to be at the bottom.
Look at convection as a form of heat transfer. To do convection, you will need the following. You need some mobile particles, so this will be things like liquids and gases. If you don't have any mobile particles, then you can't do convection. Here we have some chickpeas in a beaker of water, and we're going to bring it to the boil. By heating it up, we can follow the convection currents in the beaker or the water by watching the movements of the chickpeas. The temperature of the bottom of the beaker, the bottom of the water, is much warmer than the water in the top region of the beaker. The particles at the bottom, they gain this extra energy, this extra kinetic energy, and so the particles move further apart. When the particles move further apart, you create a low pressure zone, or a lower density. So with the water, it becomes less dense at the bottom because it's warmer. And so we know that things that are less dense will tend to rise to the surface. When it rises to the surface, it carries those chickpeas up with it to kind of demonstrate to us what is happening. So this picture here is from Wikipedia, some illustrators called Orion and Construct, 2007. They're basically illustrating the same thing that we saw in the chickpea beaker. The heat is being applied at the bottom of the beaker, and so everything that is closest to that side of the beaker is going to be very much warmer than the top. When the chickpeas and the hot water rises to the top because it's less dense, it is then exposed to the cooler atmosphere, because the air around at the top is much cooler than the air below, which was made out of the hot Bunsen burner. So that means that it can give away some of that heat energy to the cooler air particles above the surface of the water. When it does this, it loses its heat energy. It loses this movement or this kinetic energy that each particle has. And so they kind of come closer together because they're pushing each other apart less. So now that they are more dense, they then sink down to the bottom of the beaker and they go the process all over again. I hope this helps. This was convection. See you later. Bye.